Good morning. My name is Maurice Hermens. I work at the company Royal Haskoning DHV, based in the Netherlands. 6,500 people working there, of which half in the Netherlands and half abroad. We have offices like in Shanghai and Beijing, but also South Africa, Poland, for example, in the Northern America. And we're working on all kinds of consultancy and engineering subjects. Today I want to tell you about, starting with a project, but I want to tell you about urban densification with ultra-lightweight structures and building systems. And what I want to do is to start to introduce it by showing you a short movie of only 3 minutes. Then I will explain more about what you see in this movie. And in the movie you see myself and a colleague which also wrote on the paper we delivered. He was the project leader doing the real project for me.
Tonight on Extreme Engineering, building innovation with global opportunities, a preservation of a unique monument, the lightest residential building in the world, and smart buildings conquer the globe. Hello, I am Michiel Visser. An audacious plan of adding a 16-story residential building on top of a 1950s monument enhanced the social safety in the city centre of Rotterdam.
The livability of the Rotterdam city centre, especially in the evening, is improved by adding a large amount of residences in the heart of the city, on top of a monumental shopping mall. We invented an adaptation of the existing stabilizing structure, which doubled the capacity of the existing building. 117 apartments in 16 stories could be built within the released capacity by keeping the mass to a minimum.
An ultra-lightweight building on this scale has never been done before. Innovation was the key to feasibility of this project, obtaining comfortable apartments in terms of sound and vibrations, and an industrial and flexible building without a substantial mass.
We developed an IKEA-like building package with standard elements that allow for customer-driven design and specific assembly of customized apartments.
The concept is universal and offers lots of international potential. Think of dense cities like Shanghai, Singapore or Sao Paulo that keep growing but have scarcity of building space. Lightweight building transforms non-suitable building space into suitable building space, such as building on roofs, above highways, railroads and on water.
In developing cities like Jakarta, Cape Town and Ho Chi Minh, there is still space available. Here, the opportunity of lightweight building lies in easy assembly of the Lego-like building system by local builders, and in integrating local materials and knowledge without compromising the aimed high quality and comfort. Lightweight building embodies many universal and sustainable benefits in the built environment. Densify cities, enhance social safety and reduce carbon dioxide emission, pollution and material use.
The benefits of lightweight building differ around the globe, depending on local circumstances and specific priorities. One aspect always prevails. It's nice to have a place to feel at home. Thank you for watching. Until next time.
So that was in very brief what the project is about, and I will explain more about the project. But first I would like to tell you how we came to this idea of this project in the context of vertical expansions, projects of our own, but also of other companies. And then, after describing the case project, it's a realized project. I will give also a look forward about the possibilities. Well, what we started with is the idea of urban densification. Building space is becoming scarcer and scarcer, so we're looking for multiple use of space, of building space. What you can think about is building on infrastructure, on water, on or above buildings. But what is also important in the idea is that it's good to preserve existing buildings, not to demolish and make new, renew, but look what you can keep and what you can do with the existing buildings. So we have different solutions for that. We see them around the world. For example, what you can do is, if you have a tunnel structure, you can span the structure. You don't build on top, but just above. You get very impressive structural elements. It's a very beautiful example of a project like that. But of course, also you have an impact on the urban environment and the cost of the big structures. Another way of thinking is keeping the existing building but protruding it, which could be like excavating almost the building and putting a new building inside with a new foundation, a new structural system, or maybe protrude the existing building with a new core and columns and putting a new building on top. But in those cases, the character of the existing building will be different, will be gone or will be different. So the most pure way for vertical expansions is really stacking buildings on top of each other. For example, this is a museum. We put on an entrance of a tunnel in Amsterdam. The tunnel is going underwater, so there is a lot of upward water pressure. And actually, we use that upward water pressure on the tunnel to be able to put the new building on top of that tunnel. But then furthermore, the tunnel has also its own foundation system for the original situation, for keeping down the tunnel wanting to go up. So there is also a foundation, and for that foundation you can use for even more vertical load-bearing capacity. And so we were able to put this 5-story museum by Renzo Piano just on top of that tunnel already laying there, already being there. But in the case project, so in the real project, the Karel Doorman, we went 1 or 2 steps further. We didn't look only at let's say, the clear and present capacity. We didn't look at the hidden capacity like in the example before. But what we did was also create more capacity by an adaptation in the existing building. First, I would like to show you a bit where we are. We're in Europe, Central Europe, the Netherlands, in Rotterdam. And Rotterdam is a harbor city. It has a bit of the character of Shanghai, I think, but much smaller. The river is really present. The ships and like I said, the harbor. The harbor was the largest harbor of the world until 2004, and then Shanghai took this position from us. Well, the other aspect is that there was a lot of relatively new buildings from the last decades. And this in Rotterdam, this was caused by the Second World War. There was a bombing and a big fire. And here you see a picture of the city center of Rotterdam just after the war, where almost all buildings were gone. Only a few were left. So there had been, in the 50s, there had been a lot of new buildings. And the new modernistic, the Dutch modernistic style was used for a lot of those buildings. So we have some relatively new monuments in the city, and the project we built on is one of those, designed by architects Van der Broek and Bakema, who also designed the Van Elle Fabriek, one of the big monuments of the modernistic style, the famous modernistic style of Holland, which is also UNESCO World Heritage project. So the city of Rotterdam wanted to keep this project. And the city of Rotterdam wanted to do something more. They wanted to densify the city center with the shops and make it more multiple use city center, add apartments, so give more liveliness and more social safety to the city center. So there had to be a substantial amount of apartments added, not only just 2, for example, but really, like I said, a substantial amount. So we started with this question: Is it possible to put 16 floors of apartments on top of an existing building, of that existing building, and using that existing building really as a foundation for the vertical loads, for the loads of the new building? And for that we used 3 approaches, 3 steps, let's say, and not really in this order. We worked on all those together, and in the end the concept came, and in the concept all those 3 approaches came together. So the steps we did was an analysis of the load-bearing system and also hidden capacities. We did this adaptation in which we separated horizontal from vertical load, so the vertical weight of the building was transferred in a different way than the horizontal, the wind loads. And because we had these constraints of the original existing building, we used an ultra-lightweight building system. In analysis, we started, of course, with the available data. There were a lot of calculations available, all calculations available of the existing building, all original drawings were available. So reinforcement dimensions were really precisely defined. And very important, we also had good reports about the foundation. We had a geotechnical service, and the advice belonging to that, the original one. But also because a new kind of pile type was used in that time, they made a test pile in that time, or some test piles, and we had reports about that. And then what we saw, what was really interesting, was that all the foundation was calculated in that time with the information known on that time before construction, but we had this calendaring drawing, we call it, from the construction period, in which we saw that the piles, driving the piles in, became, of course, this is logical, but became much more difficult after every pile. So there was a strong densification of the sand layer because of the pile driving, and we used that as a starting point. So the existing load-bearing system, it's a cast-in-situ concrete system in which columns and beams provide the lateral stability through a rigid frame action, and that's a quite common system. You can see that a lot around. Because of that reason, the column diameter from basement to top floor is fairly constant, and that's of course important if you want to put something heavy on top. If we look at the existing foundation, like I said, there were prefabricated concrete piles with a square shaft and a plus-shaped toe. And like I said before, the piles were in pile groups, and because of the pile driving, there was a great amount of soil densification during installation. So we expected the load-bearing capacity of the piles to be much higher than originally calculated. Well, then we looked at the building. We did a lot of tests. The tests start simple with just visual inspection and stuff like that. We, of course, we have. You can see in literature and also our experience is that concrete quality becomes much stronger than in the period in the lifespan of a building. And of course, we also did laboratory tests, and those laboratory tests, they showed that the concrete quality was twice the value of the original situation, of the originally accounted for. The same we did for the foundation. We made new cone penetration tests, and we did them really next to the pile groups, so we could see the pile capacity and the effect of that soil densification. Like I said before, what we did was separate the horizontal load bearing from the vertical. We added 2 new cores, for for horizontal stability, but you also need them for elevators, staircases, shafts. And we use them not only for the new building, but also for the existing building. So the existing building got supported by the new course. And that, again, delivered a double capacity in the columns for the existing building, which we could use for the new building. So to zoom into the building system on top, that's the third item. You have to use a kind of iterative approach. I will explain that in the next slides. We started with the designing, of course, with designing the structural system, and we chose let's say a hybrid of a steel frame with a timber floor and facade. But we had in mind that it would be apartments, high-end apartments, so with high demands for sound isolation and also vibrations, felt vibrations. So what we did for the sound isolation, we completely separated different apartments from each other, following the known box-in-box system principle. I mean, so we have separated walls between the apartments, the timber floor supported on rubber springs on the steel structure, and a suspended ceiling. And actually, in this project, we didn't use any concrete. This is a non-structural topping on the floor to have a minimum kind of weight for sound isolation. And then you have, like I said, the two aspects. And about acoustic isolation, there is a lot of knowledge. But on the vibration part, in this very lightweight structure, we did a lot of research. And of course, it starts with what kind of demands you have to meet. What are your target values? And it's shown in this graph. If somebody is walking on a floor in an apartment, in that same apartment, you don't want to have too much vibrations. But because it's in the same apartment, let's say the perception of nuisance is lower than if somebody would be walking in the neighboring apartment. So we had a target value of 1.6 millimeter per second as a vibration speed in the own apartment and 0.1 in the neighboring apartment. The 0.1 is a value in which almost, let's say, 50% just doesn't feel the vibration and 50% maybe just feels the vibration. So a very strict value. You shouldn't feel anything from a person walking in the neighboring apartment. For that, we did a lot of tests. After the design, we did real scale testing. And what we wanted to know, because we wanted to be able to make also improvements if the target values were not met. So what we wanted to know was how the vibration would be transferred through the system. So we did really advanced measurements, measuring on 50 points on the same time the vibration. And then you could, let's say, track the vibration through the building system from one apartment to the other. For example, this is the vibration level on the middle of the floor on one apartment. Then in the green line, you see the edge of that floor in the same apartment, the vibration already being a bit lower, or substantially lower actually. Then from the top of the floor to this point indicated here, again, that's the black line, again lower. And then from this point to the middle of the beam, so you could see a torsional effect indicated there. And with these kind of graphs, we knew where we had to improve to be able to improve also the vibration quality. And why were we doing all of this? That's because if you have a system like that, it's really difficult, or I would say impossible, to predict everything up front, how the system will act if in a dynamic way, because there's a strong relation with the damping ratios, the connection of the nodes, how they work together, and it's very difficult to predict that. We're doing a lot of research projects in Holland about that. And you can, of course, be very on the safe side, but then you would not be really able to build lightweight as we did in this project. So we work together with TNO. It's an applied research institute in Holland, and we made these kind of models, and we were looking in these models. We were looking how much of part of the building we should model. To give a good prediction, a reliable prediction of the vibration levels, but not model too much, because then you wouldn't be able to understand what is happening, and actually it's a very intensive kind of calculation. So you want to keep the part you calculate as small as possible. And after the modeling, we did a calibration with the measurements I showed before, and that's quite technical. But what's the idea is that if you look here, above was the original model compared in blue lines compared with the measured values. And for example, here in the red area, you see that the measured values were really higher than the model gave. And also here, that's the case. The blue line and the gray line, there is a big difference. And especially in the first eigenfrequencies, the first frequencies are most important, so that's where we zoomed into. And after calibrating, we just kept on tuning damping ratios and the behavior of nodes until the model and the measurements were close enough together. So we knew that we had a good model for designing the adaptations. Well, so then we designed these adaptations. I will not zoom into that, but the results were good. We had this. We reached this high level of comfort, the low transfer of vibrations, and our client visiting the project said he had a sense in the building. He had a sense of a concrete building. So I think that was the best thing to hear possible. Well, what is important, I think, is that I showed you the project, but the approach I tried to show you also the kind of approach we used, and this approach can be used in a lot of different situations. And during the last years, this project was delivered in 2012. And also before that time, I already saw a lot of buildings which would be suitable for the same kind of approach. And of course, actually, I have to be honest, we didn't, in 2002 when we started with the project, sustainability was not so much an item as now. So we didn't start with this idea of sustainability, but we can say that it has really a high level of sustainability. We have really low material use, a minimal nuisance for the surroundings, and a reduction of pollution. And we make a very adaptable building. This was spoken about before. I don't know if you know the Dutch soccer player Robin van Persie. He wanted to buy not one apartment in the top, but he wanted to have three and wanted to connect them. After the building was already constructed, was already ready. And it was very simple to just connect all those three apartments to one big apartment with no walls in between, etc. So what are the opportunities? I think that's really clear. But like I said, on existing building, but also on floating buildings, you can use this kind of lightweight structures. But also you could use the concept in like developing countries, using the local materials and local people, local craftsmanship. Well, I think I already addressed this in general, so I would like to conclude with this. Thank you.